fun though, so I recommend it, but it is optional. Okay, I'm gonna give everyone another minute because I was late. Okay, let's get started. So we're going to talk about software transactional memory today. But first, I'm just going to finish off the very last part of the previous lecture, which was about memory models. And so we had just on Monday talked about what x86's total store order memory model is, right? And this told us what happens when you run assembly instruction on your processor. And, there's a race between several cores. What are possibly acceptable outcomes. And we talked about the existence of write buffers and how that meant that you could see a write from another thread before your write became visible to that thread. So that's cool. That's all about the silicon, and you might be wondering if that's the only place you have to care about a memory model. But unfortunately, it's not. When you write in any sort of high-level language, and that includes C, C has a memory model as well. But also, more importantly, in higher-level languages like Java, where there's a substantial, compilation pipeline that runs before you actually get to actual assembly code. There is another problem which can cause sort of unexpected behavior when your programs are running concurrently, and that's your compiler might reorder instructions. It might move things around and cause your result to look differently on other threads. So remember I said that concurrency breaks abstraction barriers. So here's a very nasty abstraction barrier that compilation breaks, which is that when I have a function, and let's say like it's a pure, no, let's not say it's a pure function. Let's say it's a function and it does a bunch of mutations and reads out a bunch of variables and then returns something, right? Your compiler ordinarily is allowed to do any optimization. It's allowed to remove writes to memory. It's allowed to reorder when things happen. It's allowed to do anything so long as the observable outcome of running the function looks the same, right? So if you, for example, write a value to some memory and the compiler can prove that that memory is never ever read from again, then read from before another write happens to that memory, the compiler is allowed to elide that assignment in that situation because, there's no way anyone can see it. Maybe. That's true if you aren't running things concurrently. If you have multiple threads, then another thread could see that intermediate value in the meantime. And now we have to talk about whether or not it is acceptable for the compiler to remove the store in that situation. Hint, it is. So the memory model basically says under what circumstances optimizations by the compiler are allowed. Is the compiler allowed to reorder these two stores? If it's not allowed to, then there should be something in the memory model that says, this would be violated. And if the reordering doesn't violate any of the constraints set down by the memory model, then it is allowed to be done by the compiler. And sort of the name of the game is the compiler wants to define a memory model that gives them enough wiggle room so that they can do a bunch of optimizations and get fast code without totally destroying programmers' expectations about what programs are going to do. Right? So the question is, what optimizations are acceptable? If I optimize some code, that will affect what other threads can see. So what are other threads allowed to see in this situation? And similarly, when there is a data race, because sort of one of the big points of having a memory model is there might be data races in our program, right? Because programmers are going to use multiple threads. They may not do locking correctly. And so it will happen. And especially if you're in a language like the JVM, where you're hey, in principle, I can run untrusted code on the JVM, then you need to give enough guarantees so that just having a data race doesn't cause an exploitable bug where they can load up some arbitrary shellcode and then execute it on your system. And the JVM does give this guarantee. It doesn't give very many guarantees about what you will see, but it will guarantee that the JVM won't segfault when there's a data race. Okay, so how is the memory model for Java set up? So to do this, I have to introduce a bunch of concepts. So individually, these concepts are not too complicated, but they're going to constitute the backbone of what it means to have a data race in Java. So the first thing I need to talk about is this relation between statements called happens before. This is very simple. A given statement happens before another one if in the source code that statement exists before that other statement, right? So x equals 1 happens before y equals 2 in this program. There's also another relation called synchronizes with, and this just refers to explicit locking operations in Java. So for example, when I lock an object and then I unlock an object, then this establishes a synchronization between, when I lock an object, when I say lock an object or unlock an object from one thread and then unlock/lock the object from another thread, that establishes a synchronization between these two threads, right? So we've got these two threads. We have a thread number 1 that first gets the lock on M, and then when it unlocks it, thread 2 gets the lock and then runs some other stuff on it. So there's a synchronization between this unlock and the lock, because the whole point of the lock is to enforce exclusion between these two threads on the critical region. So we also say when there is a synchronization, when it so happens that there's a unlock and a lock paired up in this way, there's also a happens before relation in the situation, right? So not only can I say that this lock M happens before x equals 1, but I can also say this unlock M happens before this lock M. And because happens before is transitive, I can now say in this execution of the program, x equals 1 happens before I equals x, right? Ordinarily, without the locking, there would be no relationship between thread 1 and thread 2 because, happens before is just a source code concept. But because there is synchronization, that establishes this happens before relationship. Okay, so one more thing. There's one last thing that Java has. Java has this volatile keyword. And people, this volatile is this kind of very mysterious thing. It's what exactly does volatile do? Well, the high-level explanation is volatile just lets you write to a variable, and that write is guaranteed not to get optimized away or anything like that. But what does it really do? And the answer is, in fact, whenever you do writes or reads to a volatile variable, those also establish happens before relationships between all of the threads in question, right? So there will be some sequence of operations on that variable, and all of those sequences will be well ordered in some sense. This is not, C volatiles actually do something completely different. This is a lot more like an atomic variable in C parlance. So what's the point about defining this happens before relation? Well, the point of defining the happens before relation is we need to define precisely what is a data race. And so in Java, a data race is when I have two accesses where at least one of which is a write from different threads which aren't related to each other by the happens before relationship, right? So that a data race would be, for example, this example, but without the locking, because x equals 1, x gets accessed in one thread, it gets written to in one thread, it gets read from another thread, and if there's no synchronization between the threads, I can't establish this happens before relation, and that's precisely what a data race is. And then what Java says is if there are no data races in your program, then the program will act as if it is sequentially consistent. Where sequential consistency, recall, was that model where you each instruction you run runs as if it was just one instruction by itself. So basically there is whatever the program does is indistinguishable from this case. there's a question which is, does happens before make sure that thread 2 would not acquire lock before thread 1 in the previous example? So not quite. That's what the lock's job is, right? The lock's job is to make sure that you can't lock M while another thread still has a lock on the object. And the fact that it does that is why Java says it's permissible to then establish this happens before relationship between the unlock and lock pair. And then I said something about, and then the JVM needs to like give some guarantee about what happens if you do have a data race. And there's a very complicated description in the JVM language description. I'm not going to tell you it right now, but there's like this stuff about like values can't appear out of thin air, and we're not going to segfault. But other than that, Java gives very few guarantees about what happens in data races. So here's an example where the original example, right, where I had x and y start off as 0, and then we assign x equal to 1 and y equal to 1 in a different thread, and then we read out y and x on the other threads, right? So we've got this data race here, and the data race simply means Java can do whatever they want. And in fact, temp1 being 0 and temp2 being 0 is an acceptable outcome in this case. So unlike x86 TSO, where we reasoned about it using these buffers, and we're like, oh, well, if something gets stuck in the right buffer, that can lead to the situation where the temporaries both are 0. In this situation, Java doesn't give an explanation for what happened. It just said, you violated the data race, and therefore I'm allowed to do whatever I want. Not everything, and not whatever I want, but I'm allowed to do like weird and arbitrary things. I want to give a very interesting example before we move on to software transactional memory. So this example is the so-called double-checked locking. So this is like a sort of very attractive idea that people come up with when they're like, oh, wow, locks are expensive, so I don't want to take out locks. And it doesn't work. And we're going to explain why it doesn't work based on what we just talked about now. So the idea behind double-checked locking is that we've got some object that we want to initialize, and it starts off as null. And so we would like to initialize it exactly once. So that's where the locking comes into play. But we have this idea that locks are expensive, and I don't want to have to keep taking out that lock when I read out the object. So the idea here is, okay, well, let's first test if the instance is null. And if the instance is not null, then I can just directly return it without taking out a lock. But if it is null, then I will take out the lock on this object and then, finally check if the instance is null and allocate it in that case. And, people who are, have sequential consistency on the brain might be thinking to themselves, this seems like it should work, right? Like there should not be any possible bug in this program. But that's not how Java works, right? Because remember, there's a compiler going on behind the scenes, and you don't know what the compiler is going to do. And so if you don't guarantee there's no data races, then you don't know what this code is going to do. And there is a data race in this code. Let's imagine that we have two threads, and they race to acquire the instance before it's been initialized. So the first instance reads out the instance, sees that it's null, locks, and then reads out the instance again, and then starts writing data into the instance. Meanwhile, the second thread reads out the instance, and then once again notices that there isn't anything there, and then takes out the lock and then does stuff. So we do have a synchronizes with relation here, right, between the unlock and the lock. So we can establish that this read to the instance is guaranteed to be the same as this read to the happen after, say, this read to the instance, or even this write to the instance. So this read and this write have no data race, but this initial read does have a data race, right? Because there is no synchronization between the read here and the write here. And so what actually can happen is that Java is allowed to apply an optimization where it writes into the instance variable something that's non-null before initializing the object. And now we can see that actually reading out the instance is a bad idea, because when I read out the instance in thread 2, I will see that it is actually already there. It's non-null. But in fact, the object is completely uninitialized, and if I immediately try to do stuff with it, I will just get very strange errors. So double check locking is wrong, and we can figure this out by just reasoning about our program using these happen before and synchronized relationships. Because you're never allowed to do data races. You have to make sure there isn't a data race in your program. Okay, that's everything I wanted to say about memory models in Java. If there aren't any questions, we're gonna move on to software transactional memory. Questions? Okay. So let's talk about software transactional memory, and we're going to do a blast back to the Haskell universe. So these slides are based off of Simon Peyton-Jones' slides on software transactional memory. So we talked about a whole bunch of different concurrency strategies, and some of them worked better than others, but in general, most of the strategies we looked at have a basic problem, right? Which is that they don't compose. And especially if you're just writing locks and condition variables, which is what lots of languages are only going to give you, you can easily deadlock your program. You can easily mess up your notify wake ups. It's a mess. So instead of having all your libraries sort of be in this very hard to understand jumble where you have no idea whether or not your code is correct or not without reading through all the implementation details, what we want some concurrency primitive that can just let us write layered concurrency abstractions on top of it without having to worry about what the internal implementation details are, right? I want to be able to treat a library as a black box, even if that library is using some concurrency primitives. So how can I do that? So the idea behind software transactional memory is we're not going to talk in terms of these implementation concepts like locks or condition variables. Instead, we're going to replace them with a higher level concept called atomic blocks. And the idea behind an atomic block is that everything that happens inside an atomic block somehow should happen atomically. It should happen all at once or not at all, as far as other threads are concerned. And if we can do this, if we can actually implement this, then we don't have this problem, right? Because, the atomic blocks don't say anything about what locks you take or anything like that. They just say this needs to happen atomically. You can think of this a lot like database transactions, right? In a database, you can start a transaction, do a bunch of queries on it, and then end the transaction. And the database somehow arranges for this set of insertions, say, to happen all at once or not at all. And we want to bring this idea to your programming language itself. Okay. I need to wail on locks a little more. So I already ragged on them a bit in the previous lecture, but I do want to talk about some specific problems with locks because they are going to be relevant to us when we talk about STM, because STM is going to solve these problems. So let's look through a few of the problems with locks one more time. So one problem with locks are they are non-compositional. So we have this account, right? And we've got these methods for depositing and withdrawing money from them. And in Java, I could have slapped on the synchronized keyword to get them. But if I want to add a fund transfer method, which uses these two methods, because software is all about composition. If I write some functions, I should be able to use them together to build bigger programs. Well, I can't implement it this way because the withdraw and the deposit could race. Someone in the middle could do something to the accounts that makes this withdraw and deposit invalid. And nor can I slap a lock on it with the synchronized block because that will cause a deadlock if I try to transfer from A to B and also transfer from B to A at the same time, right? Because I didn't, right? Java doesn't give me any built-in way of making sure I order my locks in the correct direction. Another problem is that even if you correctly synchronize your program so that there are no data races, you can sometimes lose the forest for the trees. For example, here's some code. So I have this counter and I want to be able to increment this counter. And how do I increment a counter? Well, I read out what its current value is, and then I write back 1 plus that current value. And this program, as I've written it here, where I take out a lock to do the read and then take out a lock to do the write, is race-free. There are no data races. But it doesn't do what you want, right? Because I can lose increments if I atomize the program at this concept. So really, like, we've been talking all about these locks and critical regions, but there's a like higher level semantic question we're trying to answer, which is like what we actually want our programs to do in a concurrent setting. And another problem is that when you write, you can write programs with data races, and they actually can be okay. Like, here's this example of a counter which is incrementing, and I have another read operation on the counter. And technically, this is a data race, right? If I have a read and I also have a write, without some intervening synchronization, that is a data race. But it doesn't really matter. If I'm reading out the value of the counter from some other thread and I haven't synchronized with the original thread, I don't really, care if I get 1,000 or 1,001, right? As long as, I get some sort of reasonable snapshot of what the state of the program was at that point in time, that's good enough for the other thread, right? If you wanted an exact count at some exact point in time, you should have done a synchronization at that point. So, like, just because something doesn't have data races or because something does have data races doesn't mean it's wrong. So you can't, data races are not a semantic notion of correctness. Like, you cannot say because it has a data race, this program is wrong. You need to be reasoning at a higher level of abstraction. There's one more thing that I want to say, which is that, it's actually really, really difficult to write, correct code with locks. There's this fun example where, let's say you're writing a queue and you want this queue to work concurrently. Well, writing a queue that works correctly sequentially, that's something you learn in your freshman class, right? On data structures. You're like, what is a queue? Here's how you do a queue. It's super easy. And if you want to do this with locks, this is a publishable academic result. Getting good performance and a correct algorithm, people have written papers about this. If you want to read about this one, you can go look at simple, fast, and practical non-blocking concurrent queue algorithms. Oh my God, ridiculous. So that is a lot to ask for programmers who just want to write a system that can work in a concurrent setting and be reasonable in that case, right? So the goal, right, with atomic blocks is we want to bring back the difficulty back to just, you want to write a concurrent queue. Well, you just put atomic blocks around the operations you want to be atomic, and it's just as easy as having written the sequential code in this case. Okay, so let's talk a little bit about what I mean by the atomic block. So atomically looks a lot like synchronized. In fact, in some sense, when people use synchronized and they aren't thinking very hard about what their code does, they're sort of just pretending it is atomically, even if it's not. And then their code, has bugs because they made the wrong assumption. What we want to say is when we write things in an atomic block, we want the lines on the inside to execute as if there was no interleaved execution with anything else, right? It was as if I stopped everything else, ran all these operations, and then did it. Whereas when I write a synchronized block, right, I'm actually saying take out a lock, do some stuff, release the lock, and that's why deadlocks can happen. And so our goal is to actually implement this somehow, and get good performance out of it, right? Because I can implement atomically blocks naively. The naive implementation is I have a single global honking lock. And then whenever I do an atomically block, I take out that lock, I do some stuff, and then I release the lock. That works, right? Like you will get the atomically semantics. And also your program execution will be completely serialized, even if you could have run things in parallel. So there's some other things going on with atomically blocks as they are in Haskell. So another cool feature of atomically blocks is they are what we call all or nothing. So let's say you're like, starting off an atomic transaction, right? So you're like, withdrawing money from here, depositing money there. And then at some point in the middle of the transaction, you suddenly realize, oh my God, like there's a problem, abort. So in normal sequential code, right, you would be left with this like garbage mutated state of all the modifications you already done at that point. Inside an atomically block, if you raise an exception, we will just roll back the transaction all the way to the beginning. It'll be as if nothing had happened. And then, of course, what I already said, right? These atomic transactions are isolated, so you can't observe, someone else concurrently mutating you on the inside. And because their semantics are not tied directly to locks, you can use atomically blocks with as many variables as you want, and you won't get any deadlocks in this situation. So that's the goal. There's a question, which is, so as soon as we guarantee that each atomic block does not use any locks, isn't it that we can assign each atomic block a lock and basically lock and unlock this whenever we encounter this atomic block? Well, no. Because let's say you've got two atomically blocks and they're accessing the same mutable state. So in that case, right, I can't have separate locks for each atomically block because like that won't cause me from stomping over the other person accessing the same shared data. Okay. So let's talk about a little bit about how STM is actually implemented. So our idea is that we are going to maintain what's called a transaction log. So what do I mean by transaction log? So inside of the atomically block, there are a bunch of operations we're going to do, right? We're going to read out from some shared memory. We're going to write out to some shared memory. This is all the stuff we're going to do. And what we are, what normally would happen in this situation is we would just go off and run the code, like directly editing the memory as we go along. And then, if some other thread comes along and tries to access that data, they might see it in an inconsistent state. So the way we're going to solve this is instead we're going to maintain this transaction log, and we're not going to actually do any of the operations we said. We're just going to go ahead and write the reads and the writes we were going to do to the log. So I'm not going to edit the variable directly. Instead, I'm just going to say, okay, this is what I want to write to this variable at that time. And so as a result, everyone is, running concurrently and no one is stepping on each other's toes because, hey, they're not actually writing to shared memory. They're writing to these local logs. And now at the very end, what we will do is we're going to try to commit the log to memory. So we're going to actually try to write the results to all the variables in question. And a very simple way to implement this is to have a single global honking lock that you take out and then do the updates on. Now the trick is that you've already done all of the computation associated with the transaction, right? So literally you're just zipping through the final writes in the transaction log and moving a pointer. So the time you spend in the critical region is very short. So you get reasonable performance even though there's a global log. But there's a problem. So let's say I'm executing my stuff in my transaction. I read out, the value 10, everything's good. And then someone else goes and does an update. And the read I did from Y is no longer 5. Instead, it's 8 now. Well, if I just go ahead and try to commit my transaction as is, I will commit some incorrect data, right? Because I will have part of my transaction operating on the assumption that, y was 10, and another part of the transaction operating on the assumption that y was 7. And I'm violating that constraint on atomically blocks that says that I'm supposed to be able to, either see one situation or the other. Like the operation is atomic, I'm not allowed to see some weird intermediate state. So to solve this problem, we need one more thing. We need what's called validation. So what validation does, and by the way, this is why we recorded all the reads that we did in the transaction log. What validation does is it says, okay, before I write all these values, and I have to do this while I have the lock in question, I need to go and check that all the reads I did are actually consistent with what I saw in my transaction log, right? If I read out 10 from Y and I read out 8 from Z, I need to actually see that the values of Y and Z are still 10 and 8. If they are not, if Z is now 9, I know that my transaction log is garbage. Like, yeah, sure, I did all this compute, but in fact, the result is wrong because the inputs don't correspond to any real situation in the system. It is corresponding to some weird mishmash of all the previous transactions. And when that happens, I need to abort. I need to throw out my transaction log, and what STM will do is it'll rerun the transaction from the beginning with the new values, and hopefully successfully get it in that case. Questions about the algorithm? I forgot to check my pacing on this lecture, so I might do a worked example at the end if I have time. I'm not sure how much time I'm going to have. Questions. So to summarize, create a transaction log, then validate the transaction log before committing it to memory. If the transaction log is invalid, you just run the transaction over again. So a little history about software transactional memory. So originally it was created by this guy, Tom Knight. And since then, there are a lot of research implementations for STM. But to be honest, you probably have never heard of STM, and you probably don't want to use the libraries in those languages. And I'm going to talk a little bit about why that's the case. However, in Haskell, STM is part of the standard library, and it is used all over the place in the Haskell ecosystem. So it's highly recommended. There are some things you might have to be careful about when scaling for a lot of concurrency. But if you're in a situation where MVARs kind of don't work because you've got some complicated multi-locking situation going on, STM is your go-to guy. You should use STM. And the reason why STM works so well in Haskell is because Haskell is a purely functional programming language. And because there isn't all that much mutable state, this the functional nature of the language makes it easier to implement STM. I don't know if I'm going to talk about this later. Okay, so let's okay, I might come back to this later. I don't remember if I have a slide on it or not. Okay. So I talked about these atomically blocks. On its face, the concept is pretty simple. We just have a region, and we say, okay, whatever's in this region has to run as if it was atomic. And are we done? And well, the answer is not quite, because I told you how to replace locks with atomically blocks. But there's this other thing that we need to do, right? In most concurrent systems, we may need to handle situations where I need to wait until some condition is true, right? I need a way of blocking. And atomically block doesn't answer that question, right? All it just says is that, well, all the operations in this block happen atomically. But what if I can't finish the transaction now? I want it to wait, for example, until someone actually has dollars available in their bank account. So to do this, we need to introduce some more concepts to STM. And of course, the other question, which I will talk about at the end of this lecture, is I'm like, wow, atomics are great. they're a very easy programming model, and you might be saying to me, okay, so then why don't I see them everywhere, right? And so there are efficiency problems in some situations, and we'll talk about that near the end of this lecture. Okay, so this is my slide about why Haskell is a good match for STM. So let's talk a little bit more about STM in Haskell specifically. Yeah, throwback to the past. We gotta look at some more Haskell code. So the main implementation idea for STM is whenever I do writes to memory, I need to log those writes so that I can commit them all at once later, right? I don't want to actually write to the memory properly because that can lead to races. But in most languages, everything in your system is mutable. So like even if you're doing some sort of very basic function that like is doing a for loop, you got that loop variable and you're incrementing that loop variable, and that's a mutation, and you keep doing this mutation. And as a result, well, like one could reason and say, well, this loop variable is local. It can't possibly be visible from other threads. But in general, there's just not a good picture about what data is shared between threads and what data isn't, because most languages just don't make that distinction. And so if you want to implement STM in those languages, you're facing a pretty stiff problem, because potentially any write to memory is write to shared memory, and you have to log all of them, and that means logging is expensive in this context. But in Haskell, right, we said Haskell is purely functional, so we've got this huge amount of immutable data, and most data structures you're working with in Haskell want to be immutable. And that means that there's only a small fragment of your program which is actually the mutable data. And to be even better, right, you might have this like mutable data structure, but really what it is it's a single mutable, IO ref, and then a purely functional data structure that, you're just atomically swapping from one value to another. So there really is very little mutable state in a well-written Haskell program, and that's the only stuff you have to do logging for. And that makes life a lot simpler, because your logging can be expensive if you're not, actually logging very frequently. Another thing is that, Haskell makes a distinction between code that has side effects and code that is pure. And when you want to do transactions, you want to like limit the amount of time you're actually inside a transaction, because hey, that's the time when you could potentially race with other transactions that are going on. And so in Haskell, right, you've got this pure IO code separation, so you don't need to actually you don't actually need to do any transactions in your pure code, right? You only need to do transactions when you're modifying mutable state, or you're doing a read and then a modify of the mutable state at some later point in time. So yeah, so we said that Haskell is kind of weird, and we had to deal with a lot of weird stuff like debug trace and not being able to really understand what's going on, because Haskell insisted on not letting you mutate anywhere. And now we're gonna get the payoff. We're getting the payoff from Haskell doing this work for us. So in case you've forgotten, let's remind ourselves about this distinction between pure and IO computation, right? So if I have this Haskell program, right, when I do a computation on the string, that returns a string because it has no side effects. It's a pure computation. But writing something to the terminal, that's a side effect, right? So that has type IO. And then we talked about IO refs, right? So these are, reads and writes to variables, mutable variables, and you explicitly have to say you're doing a read or you're doing a write in these situations. And, as such, it's very clear, whenever mutation is happening in a Haskell program. right? And so just remember what we're trying to do. We're trying to put STM into Haskell, and STM is all about logging reads and writes to mutable variables, right? We don't care about immutable variables because they always are the same thing. So these are going to be precisely the places we need to do logging. Oh, I just remembered why I had this slide. Okay, so there's another problem. In traditional programming languages, when you write code that's in an atomically block, you might not only be sort of writing to shared memory, you might also actually try to like do some side effects, right? You might actually try to write to a terminal. And remember what I said, which is I said, if we run this transaction and we realize that it's invalid, I want to retry the transaction. I want to run it again from the beginning. But that's not allowed if you're going to do side effects. So we need a way to make sure that we don't accidentally replay IO actions inside of these transaction regions, right? And you can like promise, Scout's heart that I'm not going to do anything naughty inside of a transaction. But in Haskell, because there's a separation, we'll be able to ensure that you cannot do this with a type checker. Okay, so we're about to get there. So IRFs, hopefully this looks familiar, and we have explicit reads and writes. And one last thing, so this is something that I didn't tell you about, but I'm going to tell you about now. In Haskell, we have the ability to do concurrency, and the way we do concurrency in Haskell is with a function called forkIO. And what forkIO does is it takes in an IO action as an argument, and spins up a new thread and has that thread run the IO action concurrently with the rest of your program. Fork.io returns immediately, so your current thread gets to keep going. And it returns a thread ID in case you want to, for example, wait on the thread or send it a message. So here's a simple program that has a data race in Haskell because IO refs are not transactional. They're just good old-fashioned mutable references. There's no locking on them. So this has a data race, right? Because we have a new thread incrementing this variable while we have another thread reading out from this variable. And Haskell doesn't have a formal memory model, but like if you're thinking about the Java style model, that's pretty accurate, right? There's a race between these two things. There's a question, which is fork.io like fork in C? Not quite. So fork in C is a way of spawning a new process. And the way it works is you write a fork command in your code, and then basically the process like duplicates itself. And in one of them, fork returns 0, and the other one, fork returns 1. And you can use that to figure out if you're in the subprocess or not. It's kind of like, splitting the universe, and then like, you go one way or you go the other. We could do this, by the way, with continuations, right? That would be like calling the current continuation with 0 and then concurrently calling it with 1. Fork.io in Haskell doesn't do that, right? It isn't like a fork and then the rest of the code gets run 2 times. You just pass it in the action that you want to run in another thread. So it's a lot more like spawn or some of the non-fork ways of like starting off execution in another process, given some program code. We still call it fork.io in Haskell though because it's forking execution. Sorry, it's confusing. Okay, so let's see how we're going to do atomically in Haskell. So here's an attempt at a type signature for atomically. What if we make atomically a function that takes in an IO action and returns a new IO action that corresponds to having run that operation atomically? So we're going to try to fix our data race as we did before, and instead of directly calling incar inside of the fork.io, we'll wrap that IO action, that incrementing action, in an atomically block. But there are a few problems with this. So one is that the IO type in Haskell allows all sorts of side effects, right? So if we want to do retrying of transactions, that's not good because like our printing to the screen, for example, could happen multiple times if the transaction gets retried. There's another problem though, right? If I let you access IO refs inside an atomically transaction, I can also accidentally still access the IO refs outside of an atomically transaction, right? Because no one like I just reused IORefs for this example. No one told me I couldn't use them, right? I still have the old API that lets me access them directly. And so like we don't really want to allow non-transactional access to R in this case. There's a question here, which is I just initially assume for atomically, you don't want IO actions / side effects to happen at all until you commit the transaction, until you're under the global lock or whatever. Right, that's also right? So like if I just directly use the implementation of incar, that would actually just go ahead and modify the IO ref. Now, ostensibly, mumble, under an atomically block, we could try to make it do something different. But we're just going to do a different strategy to fix this problem. So our new strategy is we're going to introduce a new monad. Wow, new monad, okay? So instead of the IO monad, which is the sin bin in Haskell, like basically you can do anything you want in it. Like you can write to your screen, draw a program, fire missiles, whatever. The STM monad is going to be a restricted monad that only allows access to transactional variables. And these are the things that we're going to share between threads and can update transactionally. So now what atomically does is atomically says, okay, give me an STM action where this STM action is simply a number of reads and writes to transaction variables, and then actually run it. And the actual running of it happens in the IO monad because this is indeed involving mutable state, and so we need to actually like have some side effects when we do it. And then we will have a separate class of variables. So we won't use IORefs. We'll instead use these things called TVARs, short for transaction variables. And you can do all the same things you could have done with them with IORefs, right? You can read out a TVAR and you can write out a TVAR with a value. But importantly, these operations can only happen in the STM monad. In the same way, reading and writing IORefs could only happen in the IO monad. You couldn't do them inside of inside pure code. This reading and writing TVARs can only happen in the STM monad. So you are obligated to do these reads and writes within the context of an atomic transaction. Now, of course, you could say atomically read TVAR, and what that would do is atomically read a single TVAR. But the whole point of STM, right, is we want to build up bigger and more complicated transactions out of multiple reads and writes to various variables. Okay, so let's look at an example. And in particular, we're going to look at our previous example that was racing with IORefs. So all I've done is I've replaced all the reads and the writes and the new vars with read, write, new tvar instead of IORef. And then I needed to insert a bunch of atomically blocks to sort of basically say what I wanted, what regions of my code I wanted to be atomic. So I didn't really change the R or the S. So we're going to just say, okay, I atomically create a new transaction variable. And in my original thread, I'm going to atomically read out from the variable. But in my fork thread, I'm going to say, I want to atomically increment the variable, where the increment happens with two operations, a read tvar and a write tvar. And so I can't do arbitrary IO actions because they'll have type IO blah, but I was expecting type STM blah, where blah is whatever the variable is. So this is what the code looks like with transactions. Simple, right? Looks very similar. You've just got these atomically blocks. And yeah, STM is a monad, right? And this makes sense because when you do an STM computation, you're basically composing together various operations on the transaction variables into a big transaction that's the actual thing you want to execute atomically. STM also supports exceptions. So basically, you can throw an exception inside a transaction, and what that will do is it will, if you totally error out on the transaction, then it will just abort the transaction, and oops, I don't want anything. But fortunately, right, we were only writing things into the transaction log, so we just throw out the transaction log, and there's no rollback needed, right? We're already there. Okay, so I finally got into the point where I've explained the basic Haskell API for STM, And I now need to get to the thing that I said I was going to talk about before, which is that, we can use atomically to get rid of locks, but it doesn't tell us how to deal with blocking. So we're gonna introduce a few more special combinators to STM, and they're going to give us some of the features that we were missing previously. Let's take a look. So what do we want to do when we need to wait for some condition to be true? For example, let's imagine that we want to withdraw some money from a bank account, but if there's not enough money, we want to wait until enough money shows up. So here's an implementation of withdraw, right? So we have to read out what the current account balance is, and then we need to check if the balance has enough money. And so the first idea for STM is the way that we're going to represent blocking is we're going to add a retry combinator. What the retry combinator says is, oops, this didn't work. Let's abort the transaction and try it again, right? So if the balance is not enough, well, that sucks. Let's go ahead and retry again, right? And, in a naive implementation of retry, we would just continually loop through here, reading out the balance and then seeing if it's okay until the balance is high enough, in which case we can finish the transaction without retrying. Now, okay. Now, you don't actually want to implement it this way, right? Because you don't want to waste CPU threads uselessly checking if the variable has gotten updated or not. And now we have to remember that there was this very clever implementation strategy in STM, which said that we're going to record all of the reads that we did in the transaction. So in fact, if I am doing a test inside of an STM transaction and that led to a retry, I know that so long as none of the variables that I read in this transaction change, then this transaction will always get to that retry, and I will always expect to retry again. So as long as none of them change, I can just suspend my thread and only try to do the retry if one of the variables I read out changed. And when the variable that gets read out changed, that's when I go ahead and rerun this transaction and try again. So I think this is pretty cool, right? So there's no condition variables. We didn't need to talk about waits and notifies on some sort of business, right? The mental model you have in your head is that this thread is just busy looping on the condition until it gets there. Because that's kind of what it is. But because of the fact that we have an implementation mechanism that is logging all the reads that happen, we can do this more efficiently in this case. And the STM runtime takes care of waking up threads, and you don't have to worry about retesting the condition to see if it's valid, right? Because we retry the transaction from the very beginning. So we will check to see if the balance is indeed high enough, because maybe we got woken up and the balance is not high enough, and so we need to wait again. The other thing that is kind of nifty about retries is that they're compositional. Let's imagine that I've got some situation where I want to withdraw 3 from account 1 and 7 from account 2. Now, this just works, right? So suppose account 1 doesn't have enough funds. Then when I'm running withdraw A13, that will hit a retry, and I'll go back to the beginning of my atomically block and wait. And similarly, if account 2 doesn't have enough funds, but account 1 does, let's say, I'll hit the account 2 withdraw, that will hit a retry, and I once again go back to the beginning of my function. So I can have arbitrary sub-transactions that have whatever conditions they have, otherwise they retry, and I can just string them all together, and I'm given a transaction that will only complete if all of the conditions are true. And I didn't have to lift a finger to do it. I could just write the code that does this and get it directly. Of course, you could have done this by saying, okay, well, this transaction, here are the conditions that need to happen. And then, you try to try to build up like a full, if statement of all the things that are going on. And that actually is not a bad idea in some situations, but like it's not very compositional, right? Like you had to like move all the conditions to the front. And it also doesn't work sometimes because maybe, you need to read out a variable to find out if you want to test a condition or not. Okay, so here's another idea, and this idea is pretty cool. This is the idea of choice. So let's suppose that I want to do a transfer of $3 from either account A1 or account A2. I don't care which one it is, although I'm going to try A1 first, and if A1 doesn't have enough money, I want to try A2. So there is a combinator that does this. It's called or else. And what it says is first run the first transaction you gave me. If that transaction attempts to retry, don't immediately retry. Instead, try the second transaction. If that one also retries, then okay, fine, we'll retry. But if that one succeeds, then we can just keep going with the rest of the transaction. So choice is basically this thing that lets us, basically work over retries, right? Like, so, if you retry or else S, you get S. And if you S or else retry, you also get S. So it actually forms an algebra. And choice composes too, right? Like I can take this transaction that, is doing an or else between this withdrawals, and I can compose that with another one that is trying to withdraw, say, from A3 and A4. So like, once again, I can build up a arbitrarily complicated transaction with, like conditions and, like, oh, well, this didn't work, so try this one, as big as I want. So or else is a, building block for transactions as well. And the final thing I want to talk about is this idea about invariants. So, so this idea is that, let's say we've got some, like shared global state. And, one of the things about shared global state is often there are invariants that we expect to be upheld on that state. Like going back to this account balance business, right? A global invariant we might want to have hold universally for our program is that account balances are always greater than or equal to 0. So ordinarily, this invariant would be something you would have to sprinkle asserts everywhere in your code, right? Where like before you write out to an account value, you have to assert that the value is actually greater than or equal to 0. But SCM, we can actually do better. So SCM has this combinator called always. And what always does is it says, hey, give me some transaction that computes a Boolean. And then I will just make sure that this Boolean is always true whenever I exit from atomic region. So to express the constraint on accounts always having non-negative balance, I can allocate a new transaction variable representing the account. And then I just go ahead and say, okay, my invariant check is read out the transaction variable and then, test if it's greater than or equal to 0. And I can do whatever I want in the always block. And the idea here is there's just this pool of invariants that applies to all the TVARs in STM. And like conceptually, after every transaction, we check that all the invariants are upheld. In fact, we don't need to check every invariant, right? If an invariant reads out the value of account A1 and I have a transaction that only modifies account A2, there's no need to execute that invariant because I know it cannot possibly have failed because of the operation in question. And of course, invariants can become dead when TVARs become out of scope and, you want to garbage collect them in that case. And the implementation takes care of that. Okay. So if you're really curious for more details about how STM works in Haskell, there's a paper, Composable Memory Transactions. Highly recommended reading to learn more. Are there any questions about these three combinators that we talked about? Retry, or else, and always, right? So retry lets us do blocking by using a very simple idea of let's just retry the transaction from the beginning. Or else lets us compose up retries by saying, well, if this retries, let's try something else. and always lets us add invariants to our global memory. Yeah, and just a pitch again, right? Haskell JC ships with a complete STM implementable. It's available in the standard library, and well, I don't know. These micro benchmarks are from a long time ago, but like if you're just trying to get some like sense for what order of magnitude the TVARs are supposed to be, if you do a read or put on a TVAR, it's like 50 to 80 nanoseconds. Compared with MVARs, MVARs are like about 20 nanoseconds because they're just taking out a mutex, right? So transaction variables are more expensive than MVARs. So if your use case does work with only MVARs, for performance reasons, you might prefer to use MVARs. And so TVARs are for exactly those situations where things are a little more complicated and you need to be able to like access a lot of mutable state that is independently locked. One thing though to be careful about is in the naive implementation, which I think is still in JC. I'm not sure if they fixed this or not. But the way read TVAR works is it just goes to the transaction and looks for the last write that happened to it. So actually, it's linear in the number of transaction variables that you've touched in the transaction. So that's another thing, which is for performance reasons, don't make your transactions too big. It'll make you sad. Okay. Let me just check. Okay, yeah. Okay, so I want to return to this point that I made about STM being hard to do in mainstream languages, right? Like, this sounds pretty cool, and, like, wouldn't it be great if, say, Java had this atomic keyword that we could use to, like, instead of synchronized, it would just say, okay, this is atomic, and I don't have to worry about deadlocking myself if I, like, take out a lock on too many things. And there's a problem, right? Which is that, like, languages like Java and C++ and all of them, they don't control side effects in the type system. So there's no way for me to say, hey, you're not allowed to access this type of variable unless you're inside a transaction. There's just no way to control this. You're always allowed to do anything at any point in time. And so if you want to add STM to a traditional language, you have to have an answer for what happens when a TVAR gets accessed outside of a transaction. And then, there's like a bunch of possible ways you can do it, like weak atomicity, where, so if you don't do a transaction, then you might be able to see the intermediate state while a transaction is still writing in values. That's kind of crazy. So you could also try to like give a strong atomicity concern where whenever you access transactional state from outside a transaction, you see some consistent state in the entire universe. But of course, it costs to do that, right? Because we have to actually make sure we interact with whatever locking strategy the STM implementation does. So, it's better if you can just be Haskell and, say explicitly, what you want to be in your transaction and leave it at that. There's another question for performance. So if you are like, STM is awesome and I want to use it on everything, well, I have bad news for you, which is that it's not very fast. Like even Haskell's implementation with all the, good stuff it does, it's not that fast. It is a lot slower than just banging on IRS, right? So sort of the key to STM's practicality in Haskell is the fact that you can just use it very selectively on the small part of your system that actually needs transactions in this sense, and then sort of not use it everywhere else where you just need speed. Like the slowdown that you're going to get from doing things in STM is like 6x or more. Now, there are some, research directions, right? So, for example, there was this idea of, like a few years back that hardware might be able to do this thing called lock collision, where like there's transactional memory support directly in the hardware. Although recent news from like big chip processors like Intel have said, we're getting rid of this feature. So, oops. Like, sucks to be us. We're not getting these shiny toys to play with. But there was a research direction for investigating how to like put HCM and SCM together in this way. This slide is a lot of data. I need to update it. The other thing I want to point out is atomicity is not a silver bullet because, like, you can still mess up your concurrent code with it, right? Like, for example, you could just like not put things in as big an atomic block as it needs to be, right? If you just like, sorry, how do I want to put this? Okay, so basically, you could stuff everything into a giant atomic block, and like this would be okay. But there's a problem with doing that, which is that the larger your atomic block is, the more variables it's touching, and the more likely it is to conflict with someone else. So if you do that, and you have this really huge atomic block, you might end up in a situation where there's so much stuff going on in your system that your super large transaction never commits because it's always getting sniped by someone else moving something else from under them. Right? This should be a very familiar situation to you if you ever have worked on like a very active, say, source code control repository where you're like trying to do a massive code mod to all the files in the system. Like if tons of people are like, making changes, then you're going to keep conflicting with them. And because you have the big change and they have the small one, you're just going to be perpetually trying to resolve these conflicts. Same deal happens with atomic transactions. The example here, by the way, is a kind of interesting example where you cannot actually put these two atomic blocks together into one. So it's actually not always okay to like glob everything into one giant atomic block. And the reasoning for the example is that if you put this into one giant atomic block, then both of these threads would never ever finish because, hey, like, this is waiting for x to be 0 before it sets y to be 1. And this one is waiting for y to be 1 before it stops retrying. And as a result, even though these are ordered differently, there is no like sequence of do all this first and then do this or vice versa that gets past the retries. Not too important, but like, you have to think about what you want the spans or atomic regions to be. Granted, this is easier than having to reason about like what order I'm taking the locks out in and, blah, 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 right? But, you can't just turn your brain off. You still need to think about how your system is designed. Also, SCM can't deadlock, but that doesn't mean you're necessarily going to make progress, right? So that super huge transaction, right, you might never actually ever get around to doing it because there's just too much work going on. So although you will globally make progress in the sense that like transactions will still keep getting processed. There's never a situation where you end up with 0 transactions being progressed. One transaction may just never ever actually make it, no matter how long it runs. And that's a problem with STM, and you need, some other scheduling mechanism or, God forbid, an actual freaking lock to like, prevent this sort of starvation situation. Okay, any questions about, how atomicity is not a silver bullet? Okay, I'm ahead of schedule, so let me just give you some parting thoughts. So we're basically, wrapping up the course. I am going to talk about ownership, and I am going to do exam review, and we're going to have a fun lecture at some point. But, we've kind of gotten to the end, honestly. And like, I think it's very nice to like think about, what we learned in the first part of this class about Haskell, and then like, how to like bring these ideas into regular languages, right? And so the big idea in Haskell was we were going to separate our computation into the side effectful IO computation and the pure effect-free computation. And so the sort of situation when we're writing programming languages is that we have these two axes. So on the first axis, we have whether or not a language is useful or whether or not a language is useless, right? So a language is useful if you can actually do stuff with it. And if the language doesn't let you do anything, then that's not a very good language. But on the other hand, we have a level of danger for languages, right? Some languages let you do arbitrary things whenever you want, and you have no idea what's going on. And these are very dangerous languages that are hard to program in. And safe languages are very well ordered. They have, all sorts of, constraints, and like it's hard to make a mistake, right? So if you look at your average real-world programming language, you're going to start off in the useful and dangerous side of the quadrant, right? You're going to allow anything you want, and then like through research, through writing new tools, through people having a better understanding of how the language is put together, they are trying to move into a universe where things are safer, right? And like, there's a lot of engineering effort that's gone into, moving this. But you don't have to do that, right? You can also be like, hey, let's start off in this awesome universe where everything is safe and you can't do anything because like it's a completely useless language. And then let's start adding things gradually to, make the language more and more useful. Because the nirvana situation, right, is that you have a language that is both useful, you can actually do useful things in it, and it's also safe. You don't have to worry about, like arbitrarily, randomly, corrupting your code. And these are both valid strategies. Most people are doing plan A, but like, if you thought Haskell was a cool language and you want to look more into it, like, because you want to go to grad school or something like that, hey, over here in Haskell land, we're doing plan B, adding in things, one by one to get there. I have more slides. I forgot about these slides. Okay. Right. So plan A is anything can happen, and then you add a bunch of stuff on top. And these are all examples of all projects where people added stuff on top. And plan B, right, is you start with nothing, and you add stuff. And there's actually other examples that are not just Haskell, right? Like domain-specific languages, like SQL. These also count as like there is nothing you can do, and then people add features on top. It's no accident that like SQL databases have transactions, because it's a very limited programming language that only lets you do certain things, and that made it amenable to doing transactions. So yeah. So like, if you're stuck with an ordinary programming language, well, you might be envious of the like awesome safe universe, but at least you're getting work done. And, if you're sitting in the Haskell side of the fence, maybe you're not actually getting any work done. That's not true, right? Like you can get work done with Haskell because we moved a little bit towards the useful axis, but a lot of the, output in this sense is just ideas, like ways to do things that, you figured out because you started off being like, let's be safe by default first. Okay, so that's all I wanted to talk about today. So, hey, atomic blocks, they're cool. Think about them. Like, they're not as unlikely as you might think. You can implement them in JavaScript. That's what you're going to do in the bonus portion of the lab if you so choose to accept your mission. I'm out of time. Thanks everyone for coming, and see you all next week.